All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules as usual. First of all, please mute yourself during the talk. If you have immediate questions, you're welcome to unmute and ask. Otherwise, please use the chat room to post your questions so that we can address them in the Q&A session at the end. Second, today's seminar is open to external audience, so no classified discussion is allowed. Finally, the talk will be recorded and uploaded to our YouTube channel. Now, let me introduce our speaker. It is an honor to host Professor Guang Lin, who is currently a full professor in the Department of Mathematics and the School of Mechanical Engineering at Purdue University. He is the director of Data Science Consulting Service that performs cutting-edge research on data science and provides hands-on consulting support for data analysis and business analytics. He is also the chair of the Initiative for Data Science and Engineering Applications at College of Engineering. He received his PhD from Brown University in 2007 and worked as a research scientist at Pacific Northwest National Laboratory before joining Purdue in 2014. He has received various awards, such as the NSF Career Award, Mid-Career Sigma C Award, University Faculty Scholar, College of Science Research Award, Mathematical Bioscience Institute Early Career Award, and so today he will talk about towards third wave AI, interpretable, robust, trustworthy machine learning for diverse applications in science and engineering. Please enjoy the wonderful talk. Now, without further ado, let me hand it over to Professor Lin.
Okay. Yeah. Hello, everyone. Thanks for coming to my webinar. So today I will talk about focus on the robust and interpretable trustworthy machine learning. So the difference from other people, so we are doing is basically to be able to quantify the uncertainty in the machine learning, in particular deep learning. So like this UNet structure I want to show you is we are able to make prediction instead of just one like the prediction we are predicted the mean prediction, also the uncertainty as well. You can say our output is 2 channels. So let's first review the 4 wave of AI. So it contains 4 different waves. So this is basically is designed by the DARPA, right? So they have the 3 wave of AI. So the first is from 70s to 90s, right? So the application is like the chess, right? And the second wave from 2000 to present, so one of typical is the autonomous driving and also the AlphaGo. And the third wave is from 2020 to 30. That is we expect at perceiving, learning, and reasoning. So similar to like ChatGPT. And the fourth wave we are hope this beyond the 2030 that's able to perform any intelligent task than a human being. So let's look at some possible applications. One is using AI for image coloring. Consider we have a lot of 100 years pictures, and we can use AI to coloring them to make them become colorful pictures. That's one application. And the other one is I'm talking about is the AlphaGo using the reinforcement learning to play chess. This is from the DeepMind pictures. So this is the artificial intelligence on the autonomous driving. So for example, yeah, as long as we can get a camera in front of the vehicle, so we can capture the road conditions, then we can use it to do the control. Okay, so the following we can looking into is like my group. The main researcher direction is considered as 5 directions. So one is focus on interpretable AI. The goal is try to discover of the physical law from the noisy data. And the second direction I want to do is the UQ as a quantification for the reliable AI. And the third direction I'm working on is the privacy preserving AI for learning from the distributed sensitive data. And another one I'm focusing on doing AI for science and engineering. In particular, I'm doing AI for material discovery. And also on the education side, I was doing the AI for workforce development. So I have developed at Purdue as an impact data science education program to utilize the AI tool to help us to do the education. So on the algorithm side, so we have developed various versions of the neural network. One is we can take the multi-fidelity data to develop a neural network that can take the multi-fidelity information to make a better prediction. The second is we want to take the physical laws and the equations into our AI so that our prediction can satisfy the equations, the physical laws. So therefore, on the right-hand side, in this box, we have these PDE loss functions so that they can minimize to train the neural network. So on here, I'm doing is we developed this so-called learning operators. The idea is we want our input to independent of the resolution in time and space. So we can input the input as like different resolution of image, or different resolution of time series as input. We can make predictions, no matter of the input resolution. Traditional neural network is very limited by the number of image. If it's 225, 256 times 256, it has to be the same size, right? The last one we are working on is so-called federated operated learning. So that particularly useful for if the data is sensitive, such as like a hospital patient data. So you don't want to share between the hospital, then this federated operated learning will be very important for such kind of application. So in particular, here's outline my talk. So I will introduce how to incorporate physical knowledge and AI to design new interpretable models. Then I will talk about for multi-scale modeling, how we incorporate physical knowledge into AI. And then I will talk about interpretable AI, how to develop the personalized treatment for Alzheimer's disease prediction. And also I will talk about sparse neural architecture design with quantified uncertainty. Finally, I will talk about the scalable training large scale deep neural network. In particular, so first I will talk about incorporate physical knowledge and AI to design new interpretable model. So the focus is try to do the interpretable AI for science. So we have two publications. So you can take one is published at the Nature of Computational Science, and then the other is PLOS Computational Biology. Both about using AI to do a model for COVID-19 prediction. So let's look at how we do that. So first of all, we develop a framework that basically a framework build a trustworthy data-driven epidemiology model. So the idea is we take the data, right, and also the events happening. Then based on the data, we develop a model. And different from other people, we do the identifiability analysis so that we on the ODE level, we want to evaluate whether on the parameters inside this ODE model, whether they are identified or not. So if it is not, then we have to go back to the design model again. If yes, we go to the next step to do the sensitivity analysis. So from there, we know which parameters are important. Then we go to the model calibration to calibrate the important parameters. Then the next step we want to do is so-called model robustness analysis. The idea is, what if the data has noise, right? I want to make sure my prediction is, robust with respect to the noise. If the yes, then I can use it to do the forecast with uncertainty. Otherwise, I have to go back to the model design again, go through this loop. So this is basically the framework we developed. It's basically a general framework that work for most of the data-driven models development. So here I want to use New York City as an example. So as we know, we use New York City. We all know that the blue line represents the different events timeline that's happening at the New York City. So this blue curve represents this number of daily cases of COVID-19. So the horizontal is the time frame from February 2020 to the end of the 2020. You can see the events from the stay-at-home order to mask mandate to indoor dining reopen to vaccination. Okay, so this is all the events. So this is all the data we have. So we try to use that data, build a model. So here's the data we normally collected. So on the A is represent the number of daily case, the B is the number of daily hospitalization, the C is the number of the daily deaths, the D is the vaccine. So the light blue is the dose 1, the dark blue is dose 2. Okay, so you can say this is the data we have. We want to based on this is build the data. So here's a extended version of the epidemiology model. So traditionally called SRR model, SERR model, but we expanded so that it can incorporate particular for the COVID-19. So you can say basically it's ODE systems, right? In the systems, so basically this is called susceptible, exposed, right? I means imposed to the COVID-19, H means the hospitalization, the D means death, Q means quarantine, R means recover, okay? The A means asymptomatic, and there's a little red circle here that is the vaccine, right? Basically, if you take the vaccine, then they can take you directly to the recover. You don't need to go through the hospitalization step. Okay, so this is the model we developed. But there's some parameters are very important that we need to using the data to help us. So one of those is called the beta, this is the transmission rate, and the P and the Q are the hospitalization and the death rate. So here we treat all these parameters as a stepwise constant parameter. Using the data, we try to calibrate them. So this is the after calibration, we are able to calibrate the parameter with respect to each event. So our assumption is that after each event, this constant will change because of this New York City policy. So here is we using this model to make 3 different scenario evaluation. So for New York City, they want to reopen the dining at February 14. Yeah, we all know why it's February 14 because it's a Valentine's Day. So they want to open the indoor dining on the February 14. So therefore, we use our model, make 3 different scenarios, try to analyze the number of infected cases. On the left, we assume they just don't have the indoor dining at all. They don't reopen. In the middle column, we say we reopen indoor dining on the February 14. On the right, we say, how about we delay this opening and 1 month later to the March 14. Okay, so therefore we have 3 different kind of predictions. So the first row represents the number of daily cases. The middle row means the number of daily hospitalization. The last row is the number of deaths. Okay, so by doing that, we can run 3 different scenarios, and we can predict the number of cases with the uncertainty error bars. Then we can using this to provide the New York City government to say, so here's the prediction based on the model, right? So that they can make a decision based on this data-driven prediction. So this is one of the forecast with uncertainty and the scenarios. The last one I want to show you is we also developed so-called physical informed neural network. So the idea is that we want to develop a flexible computer tool to study model uncertainties and also incorporate data and the different models so that we can accurately fit into the data and infer model parameter and then discover the observed physics. So by doing that, we develop a family of epidemiology model. So that includes the integer order model from simple to complex, and also the fractional order model and the time delay model from simple to complex. So the idea is we want to identify which model is most appropriate in making the prediction. And also we want to account for the memory effect. So the idea of this physical informed neural network for the fractional epidemiology model. So the idea is want to develop a neural network for the prediction of our state variable U, and for the model parameter beta, P, Q, K. Also, we model them as a time-dependent parameter as well. Then all these parameters and variables, they have to satisfy a ODE. So therefore, in the loss function, we have to define the first terms on the right, so-called data loss. Basically, want to know the discrepancy between the neural network prediction versus the data we collect. and then we do L2 now. And the other so-called ODE loss or the residual loss, the idea is we want to say, okay, the residual is supposed to be 0, right? But we build this neural net, we'll plug it in back into the equation, we want to check what's the residual, we want to minimize them. So therefore we add this ODE loss. So we want to, in the total loss, we want to combine the data loss and the ODE loss together, do the minimization. Hopefully this the developed neural net will be able to have very small data loss and also very small ODE loss, so that it satisfy the ODE equations. In the meantime, it satisfy the predictive data. So here's the predicted data. So on the left, we present you, we can fit in the data accurately for the variable that we have the observation. On the right, basically in the middle, we're basically showing you, we also can discover the unobserved dynamics. But because there's no ground truth, so we are able to predict a different kind of output of the observed dynamics using different model. On the right is basically we infer the model parameters based on the different models. So here I want to introduce a little bit about the fraction order models, right? Because this model can help us to introduce the memory in the dynamics. So here is a so-called Kobuto derivative. This kappa represented the fraction order. So the kappa normally is between 0 and 1. So it's basically is integral differential equations, so you can say. So the idea is this one can describe the memory effect. So let's look at we assume our kappa will not be a constant, will be a function of time. So therefore that parameter will be highly dependent on the data. We can use data to determine what the fractional order is. So let's look at the fractional order versus the integral order. So if the kappa less than 1, right, it's gonna have a decay effect versus the integer. So the solid line is the integer model, and the dashed line is the fractional model, right? So you can say the delay effect can be described by the fractional model. Similar things for other variables too. So here's a quick summary. So here we develop a data-driven framework that can integrate the tools help us to quantify the uncertainties. And also we developed the COVID-19 model, right? And also the physical informed neural network to study the model uncertainty. So the next step I want to show you is the physical knowledge input into the AI to pretty much scale problem. So we call the neural homogenization. So this is a joint work, okay, with my postdoc and my collaborator. So this work we call it the neural homogenization based the physical informed neural network. So let's look at how the problem is defined. The motivation in this work is we want to improve the physical informed neural network. So the classical setting of the physical informed neural network, this idea is you have an equation, this LU, equal to F. The U is the unknown you want to predict, right? And the BU is the boundary condition. And we want to develop a neural network that we don't need to write a solver by our hand. So we want to using this neural network to help us to make predictions. Then we want to using a loss function. So this loss function include this residual for satisfy the equation and the residual satisfy the boundary condition. Then we minimize the whole thing. We want to give us accurate prediction. If the problem with it does not contain the multi-scale feature, normally it give you a pretty good prediction. However, let's look at one example. In this elliptic equations, there's a kappa here. It is oscillator function. So this kappa is 0.5 sine 2 pi x over epsilon plus 2. The epsilon is small, it's 1/8. So this is what the kappa looks like. Okay, if we want to using this highly oscillator function into the elliptic equation, then the exact solution will be the blue line. And if you're using the classical pin, it's gonna give you this red curve, right? So you can say it cannot capture the multi-scale feature. And also, if you look at the arrow will not, will not converge, right? So the reason behind it is because we cannot resolve the highly oscillated parameter. So therefore, it's motivated to utilize the homogenization technique. So the idea is we consider if we are solving a homogenization, highly multi-scale problem, then we can utilize the asymptotic expansion, right? That the U epsilon, we can do the perturbation analysis, right? So we can expand the U epsilon as a U0 order plus epsilon U1 order plus epsilon square U2 order, and then we go on. Then we can solve the so-called cell problem, right? So first, by solving the cell problem, we can solve the Chi-J here. The Chi-J is periodic in Y, then we solve the homogeneous equation. Here, the Aij star will be computed from here. It was using the Chi-J solved from the cell problem. So by doing that, it can elevate the problem of the classical pin. So here's the basic idea. So we want to solve step one, solve the cell problem using the physical informed neural network. Then we evaluate the homogenized coefficients. Then we solve the homogenized equation using pin. To dealing with the periodic problem, so we use the so-called oversampling techniques. So we sample beyond the computational domain, right, to have more points so that we match the here, assume this is a boundary, right? We sample on both sides so that we want to the yellow matches the blue so that ensure the periodic relations. Okay, so we want to ensure the periodic mapping here. So such as this blue here will match this blue here, this yellow match with yellow. Okay, so we want to ensure the periodicity there. So therefore, in our loss function, it will contain three parts: the loss function in the equation, residual, the boundary condition residual, and also the oversampling to satisfy the periodic boundary condition. So here is an example of the 2D elliptic equations. So we're using the same setting, right? We know the classical pin will not work. Then if we're using our neural homogenization technique, which is such a highly oscillated permeability field, we can predict the reference solution very accurately. So here, basically, we want to demonstrate the arrow analysis, right? I want to show you for the arrow for the cell problem, for the Chi1 and the Chi2, and also the difference between with and without oversampling. So this blue line is without oversampling, this red line is with oversampling. So you can see with oversampling will, further improve the accuracy. So here is also the arrow for these 2D elliptic problems, right? So this basically we can show the arrow is pretty good. So here's arrow functions, right? So we also did some like transfer learning. We want to transfer the trained result to initialize the pin, but the problem is we still not be able to predict the original multi-scale problem. I think the reason is because these loss function are not two loss function are not close enough. So currently we are working on modify the pin loss so that be able to eventually predict the multi-scale problem. So here's some conclusion. So we basically developed this neural homogenization based pin to solve the multi-scale problem. And also we propose this oversampling strategy to solve the periodic boundary condition. So the third part I want to talk about is the interpretable AI for data-driven scientific discovery with uncertainty. So the question we want to ask ourselves is, can we using the data to discover the physical law? And eventually it can enable data-driven science discovery automatically. So along this line, I have developed a series paper. So this work is on the robust data-driven discovery with error bars, published at the Princeton Royal Society. And this work, we developed a Gaussian process is active learning so that it can do this active learning for physical law discovery. And then this is another paper dealing with the large noisy data. So in particular, today I will talk about Alzheimer's disease prediction. So this paper published as Nature Digital Medicine. So in particular, we are looking at the Alzheimer's disease prediction. On the right-hand side, you can see there's a X is time, Y is the biomarker. So if the biomarker is below this gray box, that means normal, and it's beyond means abnormal. So we want to predict the patient progression over time, right? So that's the goal we want to predict. So the idea is we're using a large data set, so-called ADNI biomarker data set. So there's 4 different biomarker. We want to using them to develop a model. So the first thing, so this is the framework we try to develop. So first, we basically try to initialize the ODE model. Then we conduct a sigma function, try to remove some noise in the data. Then we do the sparse learning to learn a so-called causal model. So this causal model will contain very few terms. Then we evaluate the population parameter using the database so that we can get a population data, a population model. So this model will satisfy the population of the patient. But we want to eventually develop a personalized model. So that's why we do a sensitivity analysis to get the personalized parameter using the particular patient data. Then we can develop this personalized model. Eventually, we can utilize it to personalized prediction. So here just a demonstration. We using a particular patient, so we can fit the model, and then using the particular patient data can come up with the ODE model. So you can see this is the 4 different variables are the biomarkers. So we can predict these 4 different biomarkers, the progression over time, right? We can study the critical points on the right-hand side, the equilibrium. So we can do a lot of analysis based on this model. So therefore, this kind of model is interpretable, right? We can learn a lot of things from there. And also, this is the results predictions, right? So we can predict the patient model prediction using this model compared with the data. So the next step I'm going to talk about from the application back to the neural network. So I want to talk about the sparse neural architecture design with quantified uncertainty. So in particular, so the question we want to ask is, can we develop a fast and small and accurate deep neural network with better interpretability and less demanding on the computational resource? Right. The goal is try to enable fast, interpretable, nonlinear data-driven scientific discovery. So we have a series paper to try to achieve this goal. So first, I want to talk about the Bayesian sparse learning. We have developed with a preconditioned squared gradient Markov-Chern Kalo. The first, I want to talk about the motivation. The sort of challenge associated with deep neural network, right? First, it requires heavy memory, computational power, and the cost overfitting. And also, the cost function is difficult to optimize, and a good local minimum is hard to obtain. So therefore, our objective is to do sparse learning and Bayesian approach and compute the posterior expectation and the escape shallow local optimal. So this is our objective. And to do that, here's some notations. So the entire data we're using the capital B, right? So there's if the model parameter we're using beta and the log posterior density we're using L, the true gradient, right? We're using gradient L, and if the mini batch we're using gradient L tilde. So the key components, right? We have a series of key components. We're using sparse learning Bayesian approach, empirical Bayesian method, and the adaptive stochastic gradient Langevin dynamic. And we also developed some preconditioner, and we incorporated the stochastic approximation and the pooling strategy. So this is the tool we use, try to achieve our goal. So first, let's look at the stochastic gradient descent. So as we all know, stochastic gradient is very powerful, right? It can find the map for model parameter, but the problem is it cannot capture the parameter uncertainty, so potential overfitting. So therefore, we're introducing the so-called Langevin dynamic and the stochastic gradient Langevin dynamic. So we using the Langevin diffusion with a symmetric distribution, right, to satisfy a stochastic differential equation. Based on that, so there's some advantage associated with the stochastic gradient Langevin dynamic. First, it's we can sample in the posterior to get the model uncertainty, and also we can compute the posterior expectation. So therefore, give us a more robust result. Also, it can escape local optimums to achieve better point estimate. Also, we utilize the pooling strategy to enable us to obtain a sparse deep neural network. So we basically can remove some, some neuron that has a very small magnitude. So we also developed the preconditioned stochastic Langevin dynamic. The idea is we want to update the parameter with different step size and adapt to local geometry and resulting fast conversion. So the idea is, we can utilize that to achieve residual network compression. So I want to show you is this highlighted one is our method. It can achieve if we do 90% sparsity, right? So that means we can get the state of art, right? You can see it's 91.68, right? If we our method can achieve, better than other state of art method. So you can see 91.68 accuracy, we only using 27K parameters, right? So if we compare with the state of art, right, that is using dropout, it can achieve 91.48% accuracy using the double the number of the parameters. This is state of art. So we can using half of the number of parameters, but achieve better accuracy. So this is a demonstration of our method. So also we can demonstrate you utilize this delta framework. We can do there's a high dimensional problem so that using our predictive approach is red color, it can give you the better approach comparing without using the preconditioner. So also this preconditioner can help us much faster convergence. So this red curve is using preconditioner versus the yellow one that's not using the preconditioner. So let's look at some multi-scale problem, right? So we want to, develop a neural network, right, to be able to predict the multi-phase flow. So to mimic the, multi-scale finite element method, so we developed this upscaling and downscaling framework so that if we input the permeability field, then we do a convolution, pooling, flattening, then we do the dancing, reshaping, and convolution. Then eventually we have this, we using the coarse grid solver. Eventually we do a downscaling, right? Do some reshaping. So eventually we can predict the U and V, the velocity field in the fine grid. Okay, so that's the framework we developed. So the advantage of this approach, so by comparing the dense layer neural network, you need 6 million parameters versus our approach only like 10% of the parameter, but we can achieve, much better accuracy, right? It's for like 2.13 versus the 1.79, right? So we can achieve by the compare, we can achieve using only 10% of the parameter, but can achieve better accuracy. So here basically try to demonstrate you the learning curve, right? Using our preconditioned work, it can achieve much faster convergence. And also here I want to demonstrate to you about the multi-scale, using our proposed framework and capture, right? So this is a 32-dimension problem. So on the left is true, in the middle is our work, on the right using the without preconditioner. So you can see for 32 dimension, right, our method can get a very close result compared to the true, but without preconditioner, it's hard to capture. We further increase the complexity. We're using 64-dimension problem. So you can see our method still can capture, but the without preconditioner cannot. So we improve this dimension to 128. So you can say this is our method compared to the ground truth. And if you look at this without preconditioner, it totally become white noise. So in summary, so we basically introduce a method that can do stochastic gradient Markov achievement column. It can capture this sparse neural network. Also, it can provide us sparse learning with uncertainty, can provide us the error bar, and also it can achieve the state-of-art compression and outperform the existing method. The following talk, I'm going to talk about a very common issue in deep learning is how to find the global minimum. Okay, that's obviously a problem because it's a non-convex problem. The reason because loss landscape is very complicated. So it's like rough like a mountain valley. So how to find the global minimum is very tricky. So let's look at a video. So how the gradient descent fail. So if you say this started the gradient descent, it's gonna stop here, right? So because here there's a local minimum, right? The gradient descent will not be able to escape. However, the global answer is here, the green area. Okay, so that's make it difficult. So that's the motivation. My last part is try to develop a scalable training of large scale deep neural network. So the question is, how can we design efficient, optimization or sampling algorithm to be able to train a large scale neural network? And also the goal is to enable fast training of large scale deep neural network. So along this line, we develop a series of papers. So let's first look at how we do that. Our tool is to, I'm going to introduce a series of tools. The first tool I want to talk about is using the stochastic gradient Monte Carlo. Let's look at what the stochastic Langevin dynamic can do. So assume the global minimum is in the middle. I try to do the sampling Langevin dynamic. I want to say whether I have a 9 of a local minimum here. I want to see whether I can fast converge into the global ones. Okay, so here's the video to do that. So here basically show the number of iterations. So you can see the sampling, right? It can, okay, I'm in the first local minimum. It take samples. It take a while to jump to the second one. It's still going to take a while. Theoretically, stochastic Langevin dynamic will achieve the global minimum, but they're going to take a long time. You can say it's still trapped in the second one, right? You can see almost a million sample, right? It's still trapped in the second one. Okay, so you can say it's a very take a lot of times to be able to achieve the global convergence. So therefore, it motivates to develop a so-called replica exchange Markov achievement column. But if we blindly using this technique, we're gonna run into some trouble. So therefore, we develop a new method called the replica exchange SGLD. So in this work, right? So we have two chains. One is low temperature, the other high temperature. The top one means this is the high temperature, this is the low temperature. So we have two temperatures, so we run two Markov chain. And then we want to swamp this rate with a probability to do the two particle swamp. So basically it's a jumper process included in this Markov process. So the basic idea is we have two chains, right? So one, you can think about we have a red team and a blue team. This red team gonna take the helicopter, go around the valley, find the the local minimum. Once it find this a good spot, then ask another team, this blue team, riding a bicycle, do the exploration. Okay, so therefore we have two teams. Okay, one is do the exploration, it's a red team, and the other team doing the exploitation. So that's the blue team. So by doing these two teams, hopefully it can give us, finding this global minimum very quickly. these two teams gonna exchange the information through the swamping. Okay, so that's the basic idea of the replica exchange. So, however, because of training the neural network on the mini batch setting, so therefore, if we do the swamping rate based on the textbook, we're gonna run into problem because it leads to large bias create from the mini batch. So therefore, we have to do some bias correction. So this is therefore we have to come up with this suggested unbiased swamping rate. So this is the this yellow color is the correction term to correct this biased swamping rate. So this is our original contribution in this part. By doing that, I want to demonstrate you the difference compared to Stochastic gradient versus replica exchange. So I want to show you this traditional one versus this. You can see the difference very quickly, right? So after 5,000 iteration, we already can capture the global minimum versus 1 million, to capture the global, right? So you can say also if you can see there's a very light dark color, So this basically idea is we can explore the 9 state very quickly. We can visit every local minimum, right? In very quickly. So we can visit each part of the valley compared to the stochastic Lagrangian dynamic. So this is our contribution in this work. So here is basically trying to show you the acceleration, why the replica exchange, right? So the black one is stochastic gradient Lagrangian dynamic, and then this blue one is replica exchange. So this distance showing you the acceleration in the western two distance. So in summary, so we developed this replica change, stochastic gradient Markov chain. So we show a potential, exponential acceleration, the convergence. And then we also developed this the various reduction technique so that can help us the further convergence. Okay, so here is some reference I want to show you. Okay, so there's the paper that we have published. So finally, I want to leave some room for the discussion. So I want to end my talk by quote from the winner, because I had to work in the closest possible ways with physics and engineer. So I knew that our data can never be precise. Thank you.
Yeah, thanks for the wonderful talk, Professor Lin. So let's start our Q&A section. Now we don't have any questions yet, but if the audience have a question, please feel free to unmute yourself. Okay, as we give the audience a moment to gather their thoughts, I will jump in and with a question to kick things off, but please bear with me if it seems like straightforward. Maybe I can ask a very basic, fundamental question about the PIN for the multi-scale problems first. So I saw like the loss functions, you include the PDE loss, the boundary loss, and the oversampling. So are there any study or any tricks on how the weights should be adjusted and how they affect the solution accuracy overall?
You mean from the boundary condition or from the solution, from the?
Yeah. So there are 3 weights parameters like W1, W2, and W3 in loss function. So how do you like pick them to make sure the solution you compute is like accurate?
Oh, okay. So yeah, this is what so basically we have in front of each loss we have omega 1, omega 2, omega 3. So we assume the omega 1 plus omega 2 plus omega 3 equal to 1, right? We're going to tune these 3 omega. So that gives us the minimum loss.
Okay, I see.
Yeah.
So maybe I can ask a question about the Alzheimer disease. So I wonder, it's a general question, but I wonder how we can tell if the patient data set that you use is a good representative of the different demographics in the whole population in practice. Do you identify or mitigate any sampling bias in these personalized predictions?
Oh, okay. Yeah, I think that's a good question, right? first of all, this data set is already, the biggest data set we have. Okay, so that is developed by my collaborator from Duke, doctors. So yeah, so my co-author. Okay, so yeah, I understand. Yeah, your question is a very good question, right? The population, where the cover, right? So so that's why motivate us to develop a personalized treatment, right? So of course, if this person is belong to if in my data set does not contains, right, that particular group, right, then yeah, I agree with you. Then yeah, this one might not be able to give the accurate prediction. Yeah, I agree with you. Yep.
See. So maybe I'll ask one more about the the COVID-19 study. So
Yeah.
I saw you build the data-driven models for minimizing the observed data, but like, how do you monitor or maintain its performance in the real-time deployment to the, like, once you train the data, is it like static, or do you use some kind of like online adaptive method or online learning techniques to like calibrate your models when you have
Yeah,
new data coming in?
that's a very good question. Yeah, so basically it depends on, so we basically every time you have new data come in, right? So we can update the model, right? So there's many way to do that. So you can just calibrate the model parameter, because our model parameter is a time dependent functions, right? So you basically updated the model parameter, right, by minimizing the loss function, right? So that's one way, right? You also can do Bayesian way, right? Can do that too. Yeah.
So do you see like significant change of these parameters when like the whole pandemic period goes over? For example, if we transit from one variant alpha to one variant, the next variant maybe beta and delta. So do you see like significant changes in these parameters?
Yeah, I think that the parameter change depends on several things, right? One depends on the policy, right? Depends on the government, which kind of control policy. If they want to do the isolation, right? Stay-at-home order, then will be different compared to like a indoor dining reopening, right? That's one. Also, I think it's different from country to country, right? Yeah, so it also depends on, if you want to use a COVID-19 model to predict, other disease, right? It will be different too, right? So I think depends on a lot of things. Also, it has a variant, right? Because Omicron, right, will be different compared to the original, right? So it's very complicated. Yeah.
I see.
I saw in the chat there's a question
Yeah.
about SGD.
So yeah, Kunchen will ask, in the replica exchange SGLD algorithm, how is it decided when to call the explorer versus the exploiter?
Yeah, so that goes through. So we basically run the two chain in parallel. Okay, so we the things that we do the information exchange. So we always run these two things together to save time, right? So we always have two teams basically, right? These two teams gonna call each other if they have some discovery, okay? So they exchange information. So that's why you saw the swapping rate, right? So they're gonna switch locations, right? Think about it, like in that example, I have 9 different local minimum, right? So these two teams will call each other, say, here, I find good one, they come to check, then the other team will come over, okay?
Okay. Yeah. Thanks for all the awesome answers for the questions. So may I ask once more if there are any more questions from the audience? And if there are no more questions, let's thank Professor Lin again for sharing his excellent research with us.
Yeah, thank you for your time.